Thank you. So I thought I would start out with a quick review of the exam. Looking at the item analysis, the average score was 40.5 out of 50, indicating it's about where it should be, I think, in terms of an average. It says there were 21 easy questions and 6 medium questions, 14 good questions, 5 fair questions, 2 poor questions. You know about those. That's in terms of the discrimination. I may still, if there is some interest, offer some opportunity for a makeup exam, but probably what it would be basically a retake. So you have an opportunity to do it again if you, at a point later in the semester, if you feel that you weren't prepared for it and would like another chance to take it. So if anyone is interested in that, let me know. It doesn't mean that you would necessarily do better, but it means you would have another chance at it. So I'm going to go over the questions, spend a little bit of time going over the questions here, and I'll kind of skim over the ones that almost everybody got right, and stop on the ones that there were more problems with, and feel free to jump in and ask questions. And I feel like it's worth doing this because the course is more or less cumulative, and it helps to understand these things as we go into the next set of topics. And then there are some other things that we don't really cover anymore. We don't do any more sensitivity, specificity stuff. So I just want to make sure that you understand it going forward, so you don't finish this class not knowing some of these basics of probability. So starting in this first one, this one most people got right. This was let's see if I can make the text a little bit bigger here. Yeah, a little bigger. Gave you a histogram for the length of stay in a hospital. Oh, I'd like to get rid of this. That's annoying. First one was just a basic probability question. How many stayed for 8 days or more? It was just a matter of counting these up and dividing by 20. And if you wanted to double check your answer, you could count the 7 or less and make sure you get a consistent answer. Then the second one was more difficult. This was a conditional probability question. What is the probability of staying in the center for fewer than 8 days? Oh no, sorry, this is just another one. This was just 1 minus the first one. So this isn't really any harder. It's just the first one was 8 or more. The second one was 7 or fewer. So you could double check your answer here just by making sure that both of these add up to 1. Let's see, the third one was a conditional probability. And this one, so actually I see the first one almost everybody got right. The second one, there was a little more trouble. And then this one, actually, there was quite a bit of trouble with. This is a conditional probability. Given that a patient has stayed at the center for 11 or more days, what is the probability that the patient stayed for 14 days? So first part is conditional on staying for 11 or more days. That means that we're only considering this group of patients that were there for 11 or more. And then it was asking what's the probability of staying for 14 days. So that's 1 divided by this number of people, which is 5 plus 2 is 7, 8, 9, 10. So there are 10 people and 1 of them stayed, so it should be 10%. And it looks like, wait a minute, I have the wrong page there. Where is the? No, I have them out of order. So I'm not actually sure how difficult those were. So I'll just continue until I get to the next spot where I have some. Okay, and then we're into a diagnostic test question. Test that is for cancer that is 99% accurate on individuals with cancer. So what is that? What do you call that? The accuracy on the cases? Specificity. And 80% accurate on individuals without cancer. What's that? Sensitivity. So if this is then applied to a population where the prevalence of cancer is 1%, what is the positive predictive value? So this was pretty much straight out of some of the questions in the assignments and the lectures, but it is a little bit tricky. You have to apply Bayes' theorem. Well, you could either do it by applying Bayes' theorem, or you could do it by making yourself a little 2x2 table of a population that has a prevalence of 1%. If you did that, you put 1,000 people with 990 in one column and 10 in the other, and then calculated the error rates in each of those, you could get to this without actually applying Bayes' theorem. This one, I remember, tricked a few people up. If an individual receives a negative test, what is the probability that the tested patient has cancer anyways? So this is not quite the negative predictive value. It's 1 minus the negative predictive value. Well, we could go through and solve these two. It's a little bit hard to do it. Maybe I can do it in an Excel spreadsheet here. Doing it on the spot. Where is X now? Compare. Maybe an even quicker way I could do this would be, I don't know, we'll do it in Excel. I was going to call it a Bayes rule calculator and do it even more quickly, but we'll do it this way. So we had with disease, without, and then we have 10 and 990. And we have plus test, positive test, negative test. So let me see, I need to call up the so it's 99% accurate on individuals with cancer. So let's see. For those with cancer, it'll be equals B6 times 0.99, and here this will be equals B6 times 0.01. And on those without the disease, let's see, it's 80% accurate, so these ones are equals C6 times 0.8 equals C6 times 0.2. Okay, so now I can calculate the PPV, which is the probability if you have a positive test that you have the disease. So PPV is equals B3 over B3 plus C3. About 4.7%. NPV by the way, actually, if you want, I could. Are you able to see your own exam right now? I can turn that on so that you can actually see.
Yeah, that's what I was trying to
see your own exam. Let's see. Oh, is it just the menu item that's hidden? Boy, Blackboard is not making this any easier for me. Here we are. Oh, why can't you see it? Can you see the link to exams?
Yeah, but you can't, but it just like takes you out of it.
So you just don't see any exams when you click on it?
You have to.
Do you know why they can't see their exams?
It kicks us out of it. Well, it's not you then. It says, like, I click view all attempts, and then it just takes you out of it, right?
Everything looks visible to me, so I'm not sure why it's not visible. How about under my grades?
I did it on both.
I think you got it, Tony?
Right now. I have to reload the page.
Okay.
I had to turn on extra attempts. If they already made an attempt, they can't go back into it.
There's there's the visibility, like
Start new submission or view all attempts.
Probably view attempts. You don't want to start a new submission.
If you want to see your answers, you should go to the grade center.
Yeah.
And click on the grade in the grade center. But if you want to see the exam, you want to go to the exam. It should open now for you.
Right. There's a setting in there about visibility, and
Yeah, that's not one.
It wasn't the visibility setting. It was multiple attempts. and it was turned off, multiple attempts was turned off, so they only had one attempt.
I don't
Since
think
they used it already, they could go back.
Let me see.
You can't see the answer.
Can you guys see it now?
No.
No, but a
Can you
new,
open the exam?
we got, start new submission, right?
Yeah,
That
but
was
you don't want to
added
start a
on.
new
No,
submission.
obviously
That's
not.
Here, just a sec. I think this is where it's going to happen. Okay, don't need to do that.
I thought I got.
Okay, include this. Okay, I think maybe now it should appear in your grade center.
Yeah.
Okay.
Where did you get it?
Just refresh.
Exams?
Read all the time.
I also turn, you have to also turn on the answers if you want to see the grade center. Which I just did, I think.
Down to like, begin.
I now
Yeah.
have everything selected.
Can't see grade center. They used to have a focus student.
Oh, you
log
They're
on,
on the full, whatever
so
your
we
grade
can
is.
see their perspective of it.
You will attempt. Okay.
So can we see the exam and can we see the,
Got
What
it.
do you got?
your answers?
Got
No.
Thank you.
You mean no?
It worked.
Yeah.
It works now.
It's working. So you can see, if you go into the exam, you'll see it again, like you can take it again if you want to, right? Does that work?
Yeah.
You can see your answers from the grade center. Okay, and you can, that's a fresh exam or do you have your answers? Okay. Where'd you get that?
All right, so did I get that? Did I get this right? 0.047 for the positive predictive value. Negative predictive value, it is, if you receive the negative test, the probability that you do not have the disease, so it's C4 equals C4 over C4 plus C3. And 1 minus NPV is 1 minus that, so about 20%. If you receive a negative test, then the probability that the tested patient, wait a minute, I did something wrong here, equals C4 over, oh, that's the wrong thing. Thank you. That didn't make any sense. C4. Okay, that's more like it. So it's pretty discriminative. If you get a negative test, it's very unlikely that you have cancer. Any questions? Okay, now this one, lots of people were led astray here. Which of the following could provide substantial improvement in the positive predictive value of the above test. Explain your answer. So one way I could do this actually is by putting the sensitivity and specificity as cells in my spreadsheet. So instead of hard coding them in here, I go sensitivity, specificity. Okay, so the sensitivity, this is if you have the disease, the probability that you catch it. So that's the 0.99. I'll put this in here instead of hard coding. I'll put this times B11. And the second one, the negative test. Oh, sorry, I need to do that here too. Times 1 minus B11. Okay, and then the specificity is 80%, 0.8. And I'll put that in here times B12. And this is times 1 minus B12. Okay, so here's the one that we're interested in, the positive predictive value. So first of all, before we do any calculations, what's the problem? We had really low positive predictive value, only 5%. Why? So we have a test that's got very good sensitivity and pretty decent specificity, but the positive predictive value is terrible. Why? Yep.
Prevalence is really low.
The prevalence is really low. So you're applying it to a lot of people who do not have the disease, and you've got a 20% error rate among those who do not have the disease. So as long as you've got a 20% error rate in the what was it, the 99% of people who do not have the disease, it kind of doesn't matter what your accuracy is among those who do have the disease. No matter how sensitive your test is, if it's performing not great if it has a high false positive rate, of, in this case, 20% false positive rate, and you're applying it to a population with 99% of people who don't have the disease, you're going to have a low positive predictive value. So improving the sensitivity without any change in specificity? What do you think? No. Let's try that. So let's take the sensitivity. Let's put that to 1. So we're at 0.047. I change that to 100%. It hardly changes it at all to 0.048. So you've increased it from 4.76% to 4.8%. So we can't call that a substantial improvement. Improving the specificity without any change in the sensitivity. Okay, so that improves the performance on the healthy people. It lowers your false positive rate. That means, since there are fewer false positives, if you receive a positive test, you're going to be more likely to actually have the disease. So this is going to be an answer. Let's try it. Let's take the specificity and increase that to 100%. Look at that, our PPV is 100%. Even at like if we took that up to 0.99, then the PPV is 50%. 0.999, we get up to 90% PPV. So this specificity is really a limiting factor in the positive predictive value. And this is the case in all kinds of tests in real life. Their performance in the population and their tendency to give false positives, it is a function of the specificity and the prevalence. So let's take this back to 80%. So we're back to this terrible 4.7% positive predictive value. Let's apply this to a, okay, I'll put in prevalence here too. Prevalence equals 0.01. So then this is equals 1,000 times times E13. I get this right. Oops, no, times 1 minus B13. Okay. Okay, so let's apply this to a higher prevalence population. Let's say one that with a 10% risk, and now the PPV has gone up to 35%. 50% prevalence, we're up to 83%. Get the picture. So applying to a higher prevalence population makes a difference, and specificity makes a difference. By the way, I just read an article in the Washington Post this weekend about exactly this thing. An epidemiologist did a survey of physicians and basically gave them a question like this. The question was, you have a test that that is 95% accurate on positives and negatives. It has a 5% error rate. You apply it to a population with 1% prevalence of the disease. If you get a positive test, what's the probability that you have the disease? What's that?
95%.
No. And this is an answer that many doctors gave, but it is terribly disastrously wrong, because so it's kind of the first answer that comes to mind, that you have a 95% chance of having the disease, but you apply that to 1,000 people, that means you're applying it to 990 people who do not have the disease. 5% of those are wrong. What's 5% of 990? That's about 50 people. So you've called 50 people who do not have the disease. You've predicted that they have the disease. Whereas only 10 people have the disease, there's a 5% error rate. So you let's say you get all of them right. So you've got how many did I say did not have the disease that got the positive test? I said 990 times a 5% error rate was about 50 people. So we've got 50 people without the disease who got a positive test, and we've got 10 with the disease who got a positive test. So out of 60 people who got the positive test, 50 of them don't have the disease. So a positive test only means you have a 10 out of 60 chance of having the disease. So something like, 1/6, whatever that is, 17% chance of having the disease. So this is a really widespread misnomer that this kind of exposes, this article in the Post exposed, but that you all know better now. So a 95% accurate test does not mean that when you get a positive test, you have a 95% chance of having the disease. And I'll send that article around. It was good. But the other thing that it noted was that there are actually a lot of real-world diagnostic tests that have error rates of about 5%. And those, when you apply them, I think in the example, it said apply them to a population where the prevalence is like 1 in 1,000. And then it's really extreme. The positive predictive value is very low when you have a 5% false positive rate and a 1 in 1,000 disease. Okay, questions 6 to 7. Here we are. Oh yeah, lots of people got this one wrong.
That's because you said it was 3 grandparents.
Who has 3 grandparents?
Yeah. But I guess one could die.
One could die. In any given year, 1 in 3 Americans over the age of 65 will experience a fall. If you have 3 living grandparents, 1 has died over the age of 65, or maybe one of them is less than 65. Assuming that the probability of a fall for each grandparent is independent, then what is the probability that none of the 3 grandparents will experience a fall? So you could do this by going to that binomial calculator that I gave you, or because it's at the extreme of 1, there's kind of a shortcut you could do, which is, so the probability of experiencing a fall is 1 in 3. I'm going to go back to my spreadsheet. 1 over third. I have 3 of them, so the probability of 2 independent events occurring is just the product of them. The product of 3 of them, the intersection of 3 of them is the cube. So I'm going to take this to the 3rd power. So that's the probability that all fall. The probability of not having a fall is 2/3. So the probability of no one having a fall is 2/3 to the 3rd power. About 30%. Any questions? 30%, that's all you had to do. The next question, what's the probability that 1 or more will experience a fall? This one's a little bit more complicated because there are multiple ways that it can happen. You have 1 who falls and the other 2 that don't, but there are 3 different ones who could have that fall. So this one's really easier to do with the binomial calculator. How many got this one right? Man, this is really useless. It puts them in some completely different order that has nothing to do with the order of the questions. So basically, each one can occur somewhere randomly here. Maybe by the time I retire, I'll have figured out Blackboard. You want me to go through this? This is one I would do with a binomial distribution calculator. You just put n equals 3, number of successes equals 1, and the probability is 0.333.
Yeah.
That's actually
What's that?
0. It says 1 or more, so 1, 2, 3. Already
1 or more, right. So actually, yeah, 1 or more. I can just take 1 minus this answer that I had here, so it's about 70%.
Yep.
Good catch. Okay. Here, are the data n equals 100 from an RCT designed to evaluate the effectiveness of a newly developed pain reliever. Okay, what's the probability? More of these probability calculations. I know I'm going to seem callous if I say I'm tired of doing probability calculations. Does anyone want me to do this I'm happy to do it if you would like me to go through it again. What's that? No. This is one where you put in your margins and so this one is a conditional probability, the probability of experiencing a reduction given that you received the new pain reliever. So it's just this row. So it's 33 divided by 33 plus 17, 33 over 50, 66%. Probability that the patient, this trial received the new pain reliever, another conditional probability. This time you look at this column and just whichever one of these is over 66. Okay. I recall that the data analysis ones people did well on. There weren't too many problems with those. You all loaded the data set. I think everyone or almost everyone was able to calculate the mean and median and all these things. There were a few people who had trouble with the interquartile range and the first quartile. That's a matter of interpreting. The IQR, maybe that's because SPSS doesn't directly give you this. You have to take the third quartile minus the first quartile. It was pretty clear TP53 had a very strongly bimodal distribution. Yeah, skew as well. This question, I think almost everyone got these right. There were a few troubles with this one. Basically, I think grade and tumor stage were ordinal. The bulking is nominal, and the other ones are all quantitative. Okay. All right, and a few probability distribution questions. You'll get more practice with calculating probabilities. This keeps on coming up. So looking up in your normal distribution table, mean and standard deviation. So you need to convert this into a z-score. This is 48 minus 55, which is 7 over 6. That's about minus 1.17. Looking that up in your Z table, we're using Excel, and that's the left tail to the left of Z equals minus 1.166. And here, looking up two of them and taking the difference. Lots of these, this would be the reverse thing. You need to look up in your table where the 90th percentile is, turning that into a z-score and reversing that to get going from z-score to the actual number of inches. Okay, and then a couple just sort of miscellaneous questions. Yet another one for Six Flags Magic Mountain. Where is Six Flags Magic Mountain?
California.
California, okay. think the one here is called
Great Adventure.
Great Adventure, thank you. I went there for the first time this summer. It was fun. And out.
And hot, I'm assuming.
What's that?
Fun and hot.
Fun and hot, yeah. Yep.
Number 20, it was a bimodal distribution question.
Number 20.
Yeah.
Yeah, which has a bimodal distribution.
Yeah. Interestingly enough, I ran the histograms.
Yeah.
There were more than one that was bimodal.
Well,
And I asked you about it, and you were like, which one looks more bimodal? And I didn't really understand that. Like, to me, it was 3 out of the 4 were bimodal. They have more than one mode. So I didn't understand how I could determine which one was more bimodal than the other.
so keep in mind, this is not a large sample size, and I showed in one of the lecture notes some histograms from a simulated normal distribution, and it's pretty common from a simple normal distribution to get a little bump somewhere in the histogram. And all of them except for TP53, they were small little bumps. There was not any clear evidence of bimodality. Whereas TP53, there were these nice big bumps in it. It was very clearly bimodal. The other ones, I don't know if I could quickly enough actually call these up to show them. But if you call them up, think about also the number of observations in the other little bumps you saw. If it corresponds to, like, 2 or 3 or 5 people, that's not much evidence of bimodality. And especially, you see a histogram that has these things and then a little blip out here. Could be bimodal, but you can't really tell from that sample because you don't have enough of a sample in this other possible mode to tell. I mean, if you wanted to do this formally, you need to do a mixture model, a mixture of Gaussians to test if there is statistical evidence for bimodality. But when you see a distribution that has something like 50, 60, 70% of your observations in one mode and then 20, 30, 40% or something in another separated mode, that is clearly going to be bimodal.
First based on for the sample size.
Yeah, well, I could call up, I don't know if I can call up quickly enough the example from class where I had some examples of normal distributions and the histograms from them. Okay. Oh, here, we've got someone in the back here with them called up. So take a look. Can you see on the, so that looks pretty much normal, looks pretty normal. Okay, now that is a bimodal distribution. This looks pretty normal. There's a little bit of noise, but really no evidence of bimodality. But that one showing there, that is as clear as day, as clear as you will ever see evidence of a bimodal distribution. Do you agree now?
No.
No? Tell me what do you see as being bimodal?
Like
What I would invite you to do What was the sample size there? How many patients did we have? $78. Okay. 578. All right. This is a little slow. Wow, okay, this is too slow, I won't do it. There are simulators too that will show you histograms from a normal distribution. Here we go. 578. Oh, it's too large. Right. So I haven't shown a lot of detail in these, but these are all samples from a random normal distribution with a sample size of 578. And you can at least see that there is some variability in here. Like here's one where there's a pretty big drop between these two in the middle. Here's one where, you know, there's a bit of a drop and up again. So if you were really trying to overanalyze this, you might say, maybe this is a bimodal distribution. But you have to remember that what you're looking at is a sample, and there's sampling variability that causes these kinds of variations. And if I change this to let's see, let me get back my okay, I'm going to do this again with just say 50 or say 57, make it smaller. Now you can see even more variability. These are all exactly the same normal distribution. So, I mean, do you think that looks like a bimodal distribution? Because it isn't. This is just sampling variability. And that's even with a pretty big sample, 57. So, on the other hand, if I do something like R-norm 57 and R-norm 7 mean equals 3. Here's some actually bimodal ones, and even those it's a little hard to tell. So to get something really clear like that one, I'm gonna make it bigger. All right, there's a real honest to goodness bimodal distributions. They have a mean of 0 and a mean of 6 and standard deviations of 1. Both 57 in each group. That's sampling variability. It's kind of apropos since we'll be talking about, I'll be introducing sampling distributions and sampling today. Okay. Where are my slides? Okay, according to BRFSS, 58% of Americans adhere to a sedentary lifestyle. In a sample of 10, you find that 8 of them do not exercise regularly. What's the probability of finding 8 or more who are sedentary from a sample of 10? Okay, this is another, I wouldn't try to do this one without the binomial distribution calculator handy. But you could do this by calculating the probability of exactly 8, exactly 9, and exactly 10, or you could do 7 or fewer, and then 1 minus that. So again, from BRFSS, 58% of all Americans adhere to a sedentary lifestyle. What's the probability of finding 80 or more who are sedentary out of a sample of 100? So these questions were back to back just to show this effect of sampling size. And this leads nicely into sampling distributions. But both of these, this is 8 out of 10, this is 80 out of 100. Just intuitively, which do you think is more likely to happen? Which should be a higher probability? Yeah. So this is a little bit anomalous, right? Because 58% are sedentary, 8 out of 10, that's more than you expect in the population. But it's a small sample size, so there's more variability in what you observe. Whereas 100, that's somewhat bigger. This is becoming a larger sample. It's going to hew more closely to the population. So your probability of 80 out of 100, yeah, you didn't even have to calculate it. You just have to say that it's less. So this is how I'm trying to get you out of the box a little bit, where you don't have to actually calculate it, but just say that it's less. Any more questions before I move on to the lecture? Okay. We're moving on this week to sampling variability in the central limit theorem, which, as I mentioned in the announcement, is the basis for much of the inference and hypothesis testing that you're going to do. So there's some pretty concrete stuff in here. I'll talk about what is the difference between a population and a sample, and distinguish between experimental, observational, prospective, and retrospective studies, but spend most of the lecture talking about sampling distributions in the central limit theorem. And then next week, we'll start applying this to confidence intervals. And I sent out a little survey for you to guess my age today. Please go ahead and do that before next week, because I will analyze your data and use it for discussion next week, and I'm curious. So what am I talking about in populations and samples? The word sample has different meanings in different fields. In biology, it can be referring to a tissue specimen, but in statistics, it refers to a selection of individuals from the population, or a selection of observations that are sampled from the population. So if your population is the state of Massachusetts, samples would be groups of people selected from Massachusetts. Again, we use Roman letters for properties of samples, and we use Greek letters for properties of populations. So a sample mean, this is X bar, and a population mean, this is mu. And things referring to the population are sometimes called parameters, population parameters. And what inference is taking something observed from a sample and inferring about the population from that sample, from that little bit of data that you have from the population. A little bit of vocabulary. Sampling units or study units are these individuals, the elements of interest, the things that, that can be counted in the target population. So this target population is who you want to study, whereas the study population is the population from which we actually sample. So if your target population is Massachusetts, but you do phone survey, then your study population will only be the people who are willing to answer their phone to strangers. And if that systematically differs from your population, it's not just a random subset of it, this introduces what we call selection bias. And then finally, a sampling frame is just your enumeration of all of the units in the study population. So it could be, let's say, social security numbers, or something that is your list of the entire population that you use for sampling. And in general, if you are going to take a random sample, you have to have this sampling frame. If you take a sample that does not involve a sampling frame, then it's probably not a random sample. For example, if we were doing random number dialing, the sampling frame is all possible phone numbers. If you're standing in front of a mall and questioning people who come out of it, you don't really have a sampling frame. It's not a random sample. Yep.
What if you decide prior to the interview every third person or every fourth person?
So then your sampling frame is all the people who came out of the mall that day. So as long as that is your target population, then you could have an unbiased sample of that population. If your population is all the people who came out of a mall during a period of time.
They gotta come out at some time, right?
Yeah, so if the customers of that mall are your target population, then yes, you can do that. But in order to do that, you're counting, right? You're counting 1, 2, 3, 4, 5, the people who come out and catching every third one. So then you have this sampling frame that is your counting of the people coming out. So yes, just putting this down here, Greek letters for population parameters like mean and standard deviation, mu and sigma, and English alphabet for sample statistics such as X bar and S for sample mean and standard deviation. These are written down in your syllabus as well as other one. All right, some different sampling strategies. A simple random sample is one where you write down your sampling frame and then take a simple random sample of it. So this would be where, let's say if your target population was the first 1,000 people who come out of the mall, you wouldn't take every third one, you'd take a random, use a random number generator to say you, I don't know, put 1,000 numbered ping pong balls into a big roller and pick 10 of them. That is how you would get a simple random sample. So everyone has an equal and independent probability. Everyone in the population has an equal and independent probability of being sampled. Systematic sampling this doesn't exactly look like systematic. Okay, this picture is wrong. I don't know what happened to my picture here. This is just the the simple random sample again. But this is the approach that you were talking about for people walking out of the mall. Systematic random sampling is where you first select the first one and then just incrementally go from that. So you take the first and you also take the fourth and the 7th and the 10th, or if you first take the second one, then you take the 5th, the 8th, and the 11th, etc. Systematic sampling. So still, everyone has an equal probability of being sampled in this strategy. And when you analyze it, you probably treat it as a simple random sample. Stratified sampling is where we have so-called strata in the population. So we have different sort of subsets of the population who we want to treat differently and sample separately from each one of them. So we have the blue creatures, we have the restroom male figures and the restroom female figures. We first stratify them, pull them into different groups, and then sample from each of these with predefined probabilities. Now, those probabilities might be the same in each stratum, but they could be different. And at some point in your EPI studies, you will cover complex survey design. And one of the things that characterizes complex survey design is that you have strata that are sampled with different probabilities. And one reason you might do that is you have an underrepresented minority in the population that you want to get enough data from. And so you oversample from the lower prevalence strata in the population, and you undersample from the high prevalence ones. And this allows you to get better inference across all of the strata that exist in the population, as long as you account for it in your analysis. This is also something useful in observational studies and experimental studies, in that it reduces your sampling variation, because in a simple random sample, you have variability in the proportions of the strata that occur, whereas in this, if you were to take repeated samples, you would always have the same proportions of these strata. But the important thing is that everyone has a predetermined probability of being sampled. Now, cluster sampling, and this looks an awful lot like first one again. How did this happen? And why didn't I notice it? The point here, so this is not the same because I put county 1, 2, and 3 here, is that you have sort of a two-step sampling. You have groups that are clustered, in this case by sample, and you first select those clusters, such as county, and then you sample individuals from those clusters. This is a strategy that can be used, because it's not feasible to, like if you were knocking door to door, and it's not feasible to go everywhere in the state to do that, including to some town just to sample one individual. Another case is where you're testing like some intervention that is done on the level of, say, a school or some other community of people, where you first group people by those groups, those communities, those schools, sample those, and then sample the individuals. So in the case of a geographical cluster sampling, you first select, say, a county, or something finer than the the 9-digit zip code, you first select that, and then you select people within that cluster. Yes?
And would you have to sample or select the clusters randomly, or can you define characteristics that you want them to have, or would that be done?
So the question is do you have to select the clusters randomly? And the answer is yes, you have to select them randomly, but there can be a systematic component to it, just like with the stratified random sampling. So you could divide your 9-digit zips into like high income and low income ones, and then sample from those with a specified probability. So you can have a systematic component to it, but in the end, your sampling has to be random, and you have to have every one of your observational units has to have a pre-specified probability of being sampled, which can't be 0. And then there are non-probability samples, such as volunteers, patients at a cancer clinic, and other so-called samples of convenience. These are actually called convenience samples, or samples of convenience, because they're selected based on convenience for the researchers, but you do not know the probability of selection, and they tend to be very prone to selection bias. So that being said, it doesn't mean they're completely useless, but you have to be aware of this and treat any inference like calculation of p-values with an extreme grain of salt, because you don't know what the probability of individuals being sampled from your target population was. So any kind of probability calculations will be problematic. Yep.
So this is like online surveys and polls?
Online surveys and polls are a great example of this. You could ask the exact same question. If it's posted on Fox News, you get one set of answers. If it's posted on, I don't know, NBC, you get a different set of answers. And it's because of selection bias. If you take the exact survey and give it in 2 different parts of the country, you'll get different answers because you have different probabilities of selecting from the population in those settings. Yeah.
It'd be on nothing. Probably on nothing, but like, say all those news stations want to get a more accurate sample, and they visit your website on a regular basis, find the IP addresses, and then did that poll, that online poll. Would that be a better way to try to?
So could they correct it by looking at the IP addresses of where they came from? So you could make some correction by doing that, given so that if you have some correction for the fact that most of your responses are coming from some area and you already know something about like the political views from that area. But that is still really only part of it, in that you're only selecting the people who are watching the news. You're only selecting the people who are interested in watching an online survey, and you don't know what the response rate is. So when you read a scientific paper, one of the key things they will say is, out of the people selected for the sample, what was the response rate? So, if it was 50%, that's not great, but it's okay. You hope that the other 50% are not extremely different from this 50%. If you get an 80% response rate, that's quite good. If you get a 20% response rate, that's terrible. But in the case of that online survey, you don't know what the response rate is. Yep.
Would an online survey on, say, a news website always be a convenience sample, or does that depend on how you define the population?
I think it would always be a convenience sample, because you don't, for any non-convenient sample, you need to start with that sampling frame. So your list of people being targeted, and then making a selection from it. And you're not doing that in the online survey. So you don't know what your sampling frame was, and you don't know what the probability of being selected from it was. So I would say that is always a convenient sample. So yeah, I mean, I have plenty of times gotten requests from, you know, a mailing list I'm subscribed to or a magazine I'm subscribed to take part in their survey. And I don't bother, even if I'm like supportive of what they're trying to do, because I think they're useless. So I'm not going to spend my time doing it. I mean, that's what makes it not useful. I mean, if everyone filled it out, then it could be good. But at some point, I have seen literature on, you know, at what point, like with social media data, you can get some extremely large samples, and at some point, even though they're samples of convenience, they have enough coverage of the population that they start becoming useful anyways. So, you know, by the time you have 10 million people or something in there, you know, that it could still be an extremely biased sample, but it could be, you know, you have to make some other kind of arguments. It could be more representative just because of its size. Yeah.
But wouldn't that also depend a little bit on how you define the population?
Mm-hmm.
If you don't want to make an inference, the population at large, but you say, my target population is the viewership or the people who visit this website.
Sure. If you don't want to make an inference, then you don't need to consider your sample to be a sample. As long as you're not trying to infer about anyone else, as long as you're just saying, like, among the people who filled out this survey, those are the only people who matter, this percent said this. As long as you're not trying to generalize from that and say, you know, that this is more popular than this among anyone else. But that's not usually what you're trying to do. Usually you're trying to make some more general statement or some kind of inference. So just a quick example here of some geographic sampling. We've got a map here. We've put a grid over it. Each one of these little blocks is one record in our sampling frame. Here's a simple random sampling, randomly selected. A systematic sample, they're along a grid. So you can see for some objectives, this might be a better approach than simple random sampling. We don't have as many big gaps here, or we have no bigger gaps. A stratified random sample where we took the part above this river and below this river and selected a pre-specified number above and below, which is going to tend to give you fewer gaps because you're guaranteed to have a specified number on each side. Or non-probability sampling, where you're interested in somewhere and you just take your samples from there. All right, more definitions. And you'll be questioned about all of this for sure. But and this is actually a tricky one. Experimental versus observational studies. Very simple rule. For an experimental study, there has to be an intervention. So it means that you do something. You affect people's future. So a randomized controlled trial is an experiment. So normally there's randomized assignments to treatment and control groups. If we're talking about an RCT, that's because there's no control, there's no conclusions. You have to, in order to say whether there is an effect, you have to compare it to the control. These are the only way to prove causality. You can do causal inference on an observational study, but not directly prove it. Observational studies are called that because you observe, you do not intervene. Few types are a cross-sectional study, which is a snapshot of the population in time, such as NHANES, New York City HANES, Behavioral Risk Factor Surveillance System. There are lots of them. Retrospective is where you look into people's medical history and recruit them based on that history. And prospective is where you take your cohort and follow them into the future, such as the Nurses' Health Study, one that I've analyzed. And again, these cannot prove causality. They cannot prove causality through deduction, but they can provide some inference on which to infer causality. And you'll hear, I'm sure, lots about this in your epi classes. I feel it's important to say that they cannot prove it, but I don't go off the other extreme and say that you can't even infer it or trust anything from an observational study. They are, they're important, and their inference can be useful if you're appropriately skeptical. So let's see, does smoking cause lung cancer? The classic example. Experimental approaches would be to take never smokers and randomly assign them to smoking and non-smoking groups, give free cigarettes to the smoking group, and then tell them to smoke and make sure that they smoke, and then follow them for years to see who develops more lung cancer. Obviously not going to happen, so we can't do that. Another could be to randomly assign smokers to a no intervention or a cessation program and then follow them for years to see who develops more lung cancer. This can and has been done, an alternative experimental approach, but obviously a very long-term one. So this is, it takes decades to develop cancer usually. So, and cessation programs aren't completely effective, so it's not as good as just taking away people's cigarettes and putting them in a room. Observational approaches could be to survey a sample, ask whether they've been diagnosed with lung cancer and how much they smoke. So this would be a completely cross-sectional approach. Obviously, it's going to have a lot of problems to it if you don't try to make sure that those with and without lung cancer are otherwise somewhat similar to each other and compare similar people to each other, and not just older people to younger people, or other ways that they might be different between your case and your control group. The retrospective approach would be to recruit 50 cases with lung cancer and 50 controls, and then see who smokes more. And the prospective approach would be to take your cohort and give them questionnaires over time to see how much they smoke, and then see which group develops lung cancer more frequently. All right, enough definitions. I'm going to show you a bit of data and talk about populations and samples. This is an example. This is a data set, the Run 10 data set. It's in R, and it has the completion time for 16,924 runners who participated in this 10-mile run in 2009. So, little poll here. Is this a sample or a population? Put up your hand if you think that's a sample. If it's population, all right. I would say it's actually not totally clear. It depends on, if you were thinking of, say, all of the DC cherry runs over years, maybe you could think of it as a sample. But for this particular DC cherry run, we have every completion time. So if we consider this to be our target population, then this is the population. And then that mean that we calculate is mu, and there's no uncertainty in it. If we calculate an exact value, that is what the mean of the population is. Now, if we take 100 runners randomly sampled and plot those, that is a sample from this population. Is this bimodal?
No, that doesn't.
No. No, it's not bimodal. So what is a sampling distribution then? And this always takes students a bit of time to get your head wrapped around. It is the distribution of a statistic for many samples taken from one population. So the procedure is you take a sample, you calculate some statistics such as the mean, and then you repeat. You keep on taking samples, calculating the mean over and over, and that distribution of means that you see, that is the sampling distribution. And this takes some time to get your head wrapped around because even though this is really important for inference, you never get to view the sampling distribution. Unless you're simulating like I'm doing here, you're only ever going to see one data point from the sampling distribution, your sample. So it's this distribution that's very important, but that you never get to see. Fortunately, we know some things about it theoretically, so it's still useful even though you never see it directly. We know they differ from population distributions. So in this example of serum cholesterol with a population mean of 211 and a standard deviation of, I don't know, about 30, something like that. These are the means taken from samples of size 25, and it looks like this. So we've taken 25 people, calculated their mean serum cholesterol, and done that over and over. So are you surprised it looks like this? The mean is the same, but it's way skinnier. Why is that? What's that? There's less variation. Yep. Why is there less variation? Yeah, you're taking the mean of the group. So in general, the average properties of a group are less variable than the individuals that make up those groups. So no matter what it were, if it were like heights, serum cholesterol, time to finish a 10-mile running race, however much variability you have among individuals, if you take a random sample, a group of them, and average them, there's going to be less variability. It'll be closer to the population mean. So let's take, in this simulation here of the 10-mile run times, or sorry, these are just ages here. I just took the ages, made a histogram for all 16,000, and then a histogram for a random sample of 100. Here's a question. Is this histogram on the right here, is that an approximation of the population distribution or the sampling distribution? And this will get immediately at whether you get sampling distributions yet or not. Do you think it is an approximation of the population distribution? Put your hand up. All right, like 5. Do you think it's an approximation of the sampling distribution? Put your hand up. Are you unsure? Put your hand up. Okay, fair enough. So I guess first of all, does it look like this? You remember this extreme difference? Does it look like the population distribution?
Yeah.
Yeah, it does look like the population.
To be honest.
You think this is bimodal? It does. It looks like that way, right? But you have the whole population here. Is that bimodal?
No.
No. So this isn't bimodal either. That's just sampling variation. Yeah, this is important to keep in mind because you're going to analyze data sets and there are always going to be samples, probably always going to be samples. And you need to remember that it's just a sample and that if you were to go and do everything the same way again, you'd have a different sample, your histogram would look different, everything you do would give you different answers because there's sampling variation. So in this one, each of these are individuals. So this is an approximation of the population distribution. This is not a sampling distribution because I'm showing the ages of individuals, not the mean age of groups. Okay, so now is this an approximation of the population distribution? Put up your hand. Sampling distribution, put up your hand. Okay, still no one. Okay, we'll have some more chances to drive this home. But it's an approximation of the population distribution. This mean of 35 would just be one data point on the sampling distribution, not 100 data points. All right, let's get to the crux of it in the central limit theorem. The reason we're able to make inference on sampling distributions in a lot of cases, and the ones that we'll get to first at least, is because of the central limit theorem. In all cases where you make inference from a sample, it's because we know the relationship between the sampling distribution and the population. And the central limit theorem is one that is valid anytime we have large samples. So if we have a reasonably large sample, well, first, no, this is in any case. The mean of the population and the mean of the sampling distribution are identical. That is always true. Well, maybe I shouldn't say always. I'm sure that there are pathological cases of some very weird distribution where that's not the case. But in practice, this is always the case. So it means that as you take repeated samples and calculate their mean, the mean of those means is the same as the population mean. So that's not too surprising. This is surprising, though, that the standard deviation of the population is related to the standard deviation of the distribution of sample means, so the sampling distribution. And I should emphasize here that this is for large samples. This is not always true, but for large samples, this is always true. The standard deviation of the sampling distribution is equal to that of the population divided by the square root of n. Very simple formula, very general, and it always holds for large samples. Yep.
What would be considered a large sample? Is there a cutoff?
I think I say in here, rule of thumb greater than 35. So it's not actually that large, but that's an overgeneralization. It depends on how non-normal your population is, and it depends on how far away from the mean you go in your sampling distribution. The more non-normal your population, the larger a sample size you need, and the further in the tails of the sampling distribution you're interested in, the larger a sample size you need. But 35 is sort of rough rule of thumb. Yes?
Is it only for normal distribution or any distribution?
Sorry?
It's only for the normal distribution.
Good question. Is it only for the normal distribution? No. As long as you have a large sample size, and that's our third one, for large n, the shapes of the sampling distribution of means becomes normal. So no matter if your population has a uniform distribution, these are the sampling distributions for samples of size 4, 7, and 10, it becomes normal, even though the population was not normal. Here's the the runners data set, the population, the ages are kind of skewed. There's no one less than 19, but there's kind of a long tail to the right. But for sample means of, so n equals 1, this is just a smaller subset of the population. The sample means of samples of size 10, and already it looks pretty normal, right? It now looks symmetric, and it gets harder to see here because they're getting smaller and smaller, but from 25 on, these look really like normal distributions. It's just that their standard error is getting smaller and smaller because they're larger sample sizes. And the standard error is equal to the standard deviation over square root of n. So, put it all together for a random sample of size n, population mean mu, and standard deviation sigma, then the sampling distribution of those sampling means, so the means of the samples, have the following distribution. The mean is again mu, the standard deviation is this thing we call the standard error, which is equal to the population standard deviation over the square root of n. So if we know what the population standard distribution is, we know what the sampling distribution is, and vice versa. So as a note, standard error, it's just the standard deviation, but it's the standard deviation of the sampling distribution. We call it standard error to distinguish it from standard deviation, which refers to individuals. So if you ever have the question, should I show the standard error or the standard deviation? Remember that they show different things. Depends on whether you want to show the variability of individuals or your uncertainty in the mean. Roughly, it tells you how much variability to expect in your sample statistic due to sampling variability, just by chance, just by the luck of the draw. And it decreases for larger sample sizes. The larger your group, the less variable their average properties are. So the larger the sample size, the less variability in the sampling distribution, the smaller your standard error, and the closer that sample mean will tend to fall to the population mean. So yeah, how large a sample? So I said here in practice, that distribution is usually close to normal when n is at least about 30, but it depends on how normal the population distribution is, and it depends on how far out in the tails of the sampling distribution you go. So for calculating p-values of 0.0001, we'll get into those later, but any deviation from normality matters more than for a p-value of 0.05, for example. For proportions, this holds as well. The same thing, the proportion of your sampling distribution is the same as the proportion from your population. All you have to do is substitute a different formula for the standard error. And the standard deviation of the proportion is the square root of p times 1 minus p, this being the proportion. And for standard error, it's again divided by square root of n. We will be applying this to inference. I'll give you a little preview here. So for sufficiently large n, this difference in the means, so this is the sample mean minus the population mean divided by the standard error, will be a normal distribution with mean 0 and standard deviation 1. That is the z distribution. So if sigma is known, then for a given sample, you could calculate z, or vice versa. Or sorry, yeah, if sigma is known, then for a given sample, you could calculate the probability of it coming from a population with mean mu. So if x bar is many standard errors away from the mean, you would say it is improbable to have come from this population. Or if x bar is pretty close to mu relative to the standard error, you say it's plausible that it came from this sampling distribution. We will also use it for confidence intervals, and this is just a teaser. We're going to get into this in honesty next week, but I want to start you thinking about it. In this approach, you can estimate 95% confidence intervals from your estimate, given assumptions about your mean and your standard deviation. So you have one observation of x bar, and you take your middle of the z distribution, you plug in minus 1.96 and 1.96, and calculate lower and upper plausible values for mu. So this is about giving your range of uncertainty in the population mean based on an observation of a single mean from the sampling distribution. And finally, wrapping up, it's been a marathon today. This central limit theorem will form the basis for t-tests, ANOVA, confidence intervals, z-tests, because it tells us the sampling distribution for large enough n, even when we don't know the population distribution. So a few things you should know after this class. You should know about sampling distributions and population distributions, that's for sure. And know these three aspects of the central limit theorem, and beware of these general classes of studies, the experimental studies and different types of observational studies. Awesome. Any questions before we can take a 10-minute break and let Tony take over with the lab, short lab today? All right, thank you.
Should that be a short lab? We can stay late if you guys want.